All right, so the plan in this session is to talk about robotics and other applications of Scenic. So we have a few lightning talks scheduled. I'll start out talking about a little bit of what we've done here at UC Santa Cruz in robotics. Then the hope is we'll have Kaustov from USC talk about their work. He should be joining us remotely, hopefully. And Kyle tell us a bit about the indoor robotics stuff they've been doing at Berkeley. And then Mary can talk about what we've been doing in aviation. But there are lots of other domains that Scenic has been used in, like Sanjit mentioned a bunch of them. So if there are other domains people would like to talk about here, we can do that as well. One in particular that we might want to talk about railways. We have a few people from Deutsche Bahn. Actually, none of them are on here yet, so let me also make sure that they have the link. But I think they weren't going to be able to give a talk, but I'm hoping if they can at least attend part of it of the session, we can talk with them to see what they're interested in. So let me pull that up right now. So yeah, so that's the plan. Basically, we'll have, I think, 4 short talks, and then we will have time to talk about robotics, applications for Scenic generally. Then I set aside some time for us to talk about aviation too, because that's another domain people are interested in. And then maybe we can talk about railways at the end as well. Okay, so I'll start off by talking a bit about what we've done with Scenic and robotics. So I showed this example actually yesterday, but I don't know if everybody was there for that. So this is the Webots robotics simulator. And we've done a few case studies in this simulator, testing different kinds of robots. So this one I'll start running. We saw yesterday, this is a Mars rover example. Or actually, in this case, we are not plugging in any particular software for the rover. It's controlled by hand. So once this starts running, there you go. You can see you can actually press some keys here to steer the robot. So this was just a kind of proof of concept we did to show how you could use Scenic to generate interesting problems for, say, a robotic planner. So in this case, the robot is trying to get to that flag, and there's this bottleneck where it is forced to kind of crawl over this rock in the middle. So you could, the idea is you could not just test perception systems, which is largely what we did in the early days of Scenic, but generating interesting problems for a planner where it has to come up with some interesting way to solve the problem. But here we haven't actually plugged in a real planner yet. This is just, you can steer that rover by hand. And we'd like to do some case studies like this. So if you or people you know have planning systems that you're working on, where we might be able to do something interesting like this, we'd be happy to collaborate on that. Another thing that I'll mention is that in the latest version of Scenic, Scenic 3, we now have the ability to talk about 3-dimensional scenarios. We're using that fact in a little way here in some sense because we have this irregular terrain, but actually you could talk about this in the old version of Scenic as well, this example, create Scenic 3. But we have some applications in mind for robotics where 3D information is really necessary. So an example of that would be the vacuum examples that we also saw yesterday. So if I close this, so yesterday we also looked at some of these vacuum examples. So these examples where you have an indoor robot that can go under tables, for example, there you really do need to know precise shapes of objects. Oops, showing up on the wrong screen. Here we go. Oh, I realize I'm not sharing my screen here. Sorry, Kaustav, just noticed that.
No worries.
Here we go. All right. Can you see that now?
Yes. Okay. Yeah, I can see it.
Kaustav, can you see my screen now?
Yeah, I can see it. Yes, thank you.
Okay. Hopefully that's working. Oh, so great. Thank you. Okay, so like in this example, this is a Roomba example we did in the Scenic 3 paper where we're creating this living room type of environment where there's a table with some chairs, a couch, etc. And here, this green disk is the Roomba. This kind of scenario, we need to know the 3D shapes of objects because we need to know, for example, that the robot can drive under the table without intersecting it, but it can't like drive under these orange cubes. Right? So previously in Scenic, we didn't have exact shape information, so we couldn't reason about scenarios like this. But now Scenic can actually generate things where it could place this robot underneath some other objects. So here we go. I just asked it for a second scene, and in this one, you can see the robot is actually partially under the table. I can tell there. So this opens up applications for, this was a robot vacuum, but you can imagine other kinds of interesting scenarios where a robot has to move in some confined space or pick up objects with obstacles around it and so forth. And on that last note, I wanted to mention the third example we've looked at where that kind of thing is important, which is to robotic arms controlled with a reinforcement learning agent. So I just want to show a couple of slides from a master's student, Po-Hao Chen, who was working with in my group. So here's an example we did of a robotic arm. This is also simulated in Weebots. So here it's this arm with several joints and a gripper on the end. And in this case, the task we trained it for was to get to this location here without colliding with that other location there. So this is basically a toy example of a task where you have to reach and grab something while avoiding collisions with other obstacles in the environment. And so Scenic can help generate training sets for this kind of thing by randomly positioning the different obstacles and the goal objects that you're trying to pick up. So this is also an area that we'd like to pursue more in the future. Okay, that's it for my talk. So let's go on to next one. I think we'll have Kaustav up next. So I'll stop screen sharing. And if you want to go ahead, Kaustav.
Yeah, sounds good. Can you guys hear me over there? I'm not sure if microphone is working.
The audio's.
Hold on, Kaustav. We can't hear you. Just a second. Oh, the volume's up. Strange.
Is it from my end?
On my laptop. Okay, can you say something again?
Hi, can you guys hear me?
Yeah.
Okay, awesome. All right, let me share my screen real quick. All righty. I'm gonna try to present things. All right, can you guys see my screen? I think I can't hear. Okay, there's.
Yeah.
Okay, awesome. All right. Hi. Hi. Yeah. Thank you for allowing doing this amazing workshop. And I'm Costa Chakraborty. I'm a PhD student working with Professor Somil Bansal at University of Southern California, and I primarily work on safety analysis of vision-based controllers. So something that we have spoken about yesterday, today actually, the session before this was this taxinet problem where this plane is flying down the runway, and we are supposed to find out where this taxinet fails, and that is the specific example that I'm going to motivate my work towards. So what I work on specifically is this something called this closed loop system, where there are these images where the taxinet gets from the environment, and we feed that to the visual controller. And it is a CNN and a P controller in this case. And this robot is a taxinet robot, and it has this cameras on it, and it takes them. And this is a closed loop that we want to work on. And my research specifically revolves around the question of how do you find these failures, and the second is how to design the system. And this is a very short talk, so I'm just going to give you a quick sneak peek. So basically, what something that is motivated towards is something like this. So when let's say this autonomous vehicle is driving down the road and it sees this weird red looking sign, it is trained to stop at stop signs, and it thinks there's a stop sign and it stops. This is a motivating example. And what we do instead is compute something called backward reachable tubes, which are short for BRT, which is a set of all states from which the system is bound to be driven to failure. Basically, if you consider this L, this set L as the state which is a failure state, we compute this light brown state where if you start the system from this, for example, this aeroplane from this state, it was bound to enter here. So we can assure that if your system starts from within this light brown state, it is unsafe and it will fail all the time. So we essentially want to capture this light brown state. And for that, what we do is this is a top-down view of the same taxinet example that Sanjit was talking about in the previous session. And we did demarcate that these regions are failure. Basically, the plane should not veer off the runway. It should stay on the runway. So as soon as you get out here, it's a failure. And we compute the backward reachable tube of this plane system. So essentially, these red areas are the backward reachable tube. This is a projection of the X position, the theta, so cross track position across the runway and the heading. For a specific downtrack, for a specific position on the track, this is the BRT. So essentially what it means that if you start from anywhere on these red regions, you are bound to enter the failure set. and what we can do is we can actually check the images that are present on these BRT, on these red regions. And they are the ones which are actually causing the failure. So essentially, for example, this bottom right, if we start from something on that region, you'll see that the aircraft veers off the runway. And this is a very similar example that even Sanjit showed, I think. And the reason that happened is because of this pedestrian this runway marking thing that happens here. So essentially, these kind of artifacts, similar to the previous motivating example of the red signal. So these kind of artifacts, when present in the field of view of the robot, they actually, these are the kind of failure modes that we want to discover through our work on reachability. And further, from this workshop, we want to see whether we can incorporate Scenic and use different simulators to extend our work to find more failure sets in different systems. Yep, that is all from my end. If there are any questions, happy to.
Thanks, Kostav. Any questions? I can ask one, so we might have to take this offline because this might be a long question, but I'm curious how you did the backward reachability computation for the taxinet example, because it seems like you would need to model what the perception system is doing, not just the controller. And so you'd have to somehow like propagate this reachability thing through the network, or are you somehow like abstracting the network away?
So yeah, we're using we are straight up using the X-plane simulator. So in Hamilton-Jacobi reachability, the method that we use, we can compute reachable sets by using samples of the controller.
Oh, I see. So you're approximating the set using samples.
Yes, exactly.
Got it.
Yes.
Got it. Thank you.
Yeah, of course.
Any other questions? Okay, great. Thanks again, Kostav. Then let's see. Up next, we have Kai. Do you want to plug in over here?
Good.
So I'll just do this thing. All right.
Oh, are you in the Zoom meeting already?
Oh, okay.
Okay, we have to share your screen.
Right, I forgot. Let me
If you go to the conference website, the workshop is linked.
okay. Let me
To the conference website.
yeah. Forgot about that.
the original land until
Oh, I think you're in the wrong one.
too close.
You must be in the next door one.
Oh,
Let's go back to the workshop website.
works on our side, so
Yeah, and then scroll down to the schedule.
so there it is.
We're in the breakout room.
This one.
That one, yeah.
Yeah, thanks.
Sorry.
Recording in progress.
Better mute yourself or turn the sound off. There you go. And the microphone.
Okay, yeah. So I'm not talking.
I wish the next person
Yeah.
share the screen afterwards.
Okay.
Yeah, might work better.
Let me step it in on this. Let me make sure.
I would plug that in first before you try.
Yeah. No, just making sure I find the tab. Okay. Now,
But they still only have one desktop. Are you mirroring? Is that how you're gonna do it?
oh, I'm doing this one. I'm doing like this.
Okay, so you're mirroring.
Okay. Is that okay? All right. All right. So, yeah. So my name's Kai. I'm a master student in aviation and residential science working on Scenic, and today I'm going to quickly go over some of the recent work on Scenic applied to robotics. Specifically, we're going to quickly talk about the gazebo and habitat interface. Now, due to time constraints, this will be a relatively sort of high level view and very quick. So, so first of all, we want to start talking about the Scenic gazebo interface. So currently we have a Scenic gazebo template interface that is in the process of being merged into the main repo. It is a template that you can that has instruction for implementing it for your specific robot model and in your specific world model inside gazebo. And how we do plan on in the future to implement the Scenic interface to newer versions of gazebo as well as newer versions of ROS. And included in this new merge is a example implementation to the Sawyer robot, so you have an example as to how to extend the template interface to your specific robot model. So as a quick demonstration, this is what we have been able to do. I want to quickly show you what some of the stuff we've been able to do with this new interface. Now, this is the simulation showing a gazebo with a human support robot from Toyota, and Akamo Design here has provided us tremendous help in getting this done. So what happens with this thing is that we will spawn the robot at one end of the corridor, and we will spawn a table with the bottom on the other end of the corridor. The robot's task is going to navigate to the other end to grab the bottle and then come back to the starting spot while avoiding collision with the randomly generated chairs, which is also controlled by Scenic. And the special behavior that it has is that, if on its way back, if it has a bottle in its hand, it will drop the bottle if it ever comes close to a certain distance of a chair. And I think it is soon yeah. So as you can see right here, it's actually a case where the robot actually fails to avoid a collision, and it sort of backed off and ran into a chair. And then the next scenario is actually also an interesting one, where it tries to navigate to the other end of the hallway, but then it just starts to have this kind of hesitation between two paths, hesitating as to which path to take, and it sort of just gets stuck in this loop for a while before eventually it is able to sort of snap out of this loop. So sort of fast forward a bit. Yeah, so around here, it finally snaps out of this hesitation process and then proceeded on its task. Now, the following few simulations proceed in a similar way, so I will pause right here and move on to the next part. So this is a Scenic program that we use for the demo. So we won't go in detail on this, but on the left side, it is the behavior that we define to control the robot. So it is a try and interrupt block general flow that we have seen yesterday in the workshop. The try defines tells the robot to say to go to the other end of the corridor, grab the bottle, and come back. And interrupt say, if you come close to the chair, release your hand and drop the bottle. So this is a demonstration of what the try and interrupt block does. And then after it drops the bottle, it proceeds to go back to the starting position. On the right side is the basic scene description as to what the world is going to look like, the basic scene and things that we have seen yesterday. Now moving on to the second part, this is more recent. This is done essentially in the past maybe 4 or 5 months. This is the scene habitat interface we have implemented. So what we did is that we interfaced Scenic to the new MetaHabitat 3.0 simulator, which is the new version of the MetaHabitat simulator. And it is a ML and RL focused platform. So what our hope was that we can leverage this platform to perhaps apply Scenic more to the machine learning based robot domain. Now, another good thing about this platform is that it has dedicated human models that are very controllable. So we were hoping to generate some human-robot interaction scenes, which is actually what we did in one of our recent projects. So recently we had a project about the dynamic multi-objective falsification of a cyber-physical system. So for those of you not informed, that this falsification, like the presentation talked about earlier, is essentially searching for conditions that can cause system failure. So in this case, what we did is that we developed a formula that we call dynamic rulebook. This one helps us specify and falsify multiple simultaneous objectives that a system has to obey. Now, and we were eventually able to do this study using Scenic to verify. Now, the more details about this is actually, we can talk about this offline, but I will actually just move on to the experiment and demo we've done. So right here, I'm going to quickly play a demo video of the experiment we did in Habitat. What happens is that this scenario is broken down into 2 segments. The first segment happens in the bedroom, and the second segment happens in the living room. In the bedroom, the robot right here, the spot, the Boston Dynamics spot right here is the ego. It is going to try to pick up the box that is generated on the bed, while a human next to the robot is going to reach her hand around the bed. The goal right here in the first segment, there are 2 goals. The first one, the top priority one, is to avoid hitting the human hand. The second priority is to pick up the box. After picking out the box, the human is going to walk out. The robot is going to want to deliver the box to the human standing outside while avoiding the other robot that is sort of traversing around in the living room. So in the second segment, you also have a twofold objective. Top priority is to avoid damage of the other robot, which is the collision. The second priority is to deliver the actual box to the human. So right here, it's a demonstration of how cyber-physical systems, or just robots in general, have to simultaneously satisfy multiple objectives with different priorities, and those objectives can change depending on the segment of the task. So this is the simulation that we run in Habitat. So after this one, this is the Scenic program that we use. As usual, on the left side, you have the behaviors defining the code defining the behaviors of the agent. Of course, the first one, grab and deliver, is for the ego robot. The second one, reach, hand, and walk, is for the human. And the third one, traverse, is for the second robot that is walking around in the living room. On the right side is the usual definition of world space. So finally, just for completion, this is a table taken from our paper that's going to appear on RB 2024 on this work. This is just a comparison of different algorithms in general. Our falsification workflow display a comparable or better performance compared to existing samplers as well as existing workflows. So phi 1 and phi 2 is the human robot interaction experiments. The other ones are our autonomous driving ones running car. So yep, that'll be it for the presentation. Thank you.
Okay. Thank you. Okay, questions.
Yeah, for the your experiment, did you need to like program the controller or is that
Oh, the controllers are all sort of pre-built.
pre-built?
Yeah, the controller came with the simulator.
Oh, great.
They're part of the robot stack. So all Scenic did was tell you which actions to take, and the low-level controller is done by itself.
Mary, do you want to start setting up?
Yeah, no, I'm actually
Oh, you're in the
just
Zoom
making
room?
sure that this works. I think I have, for somebody else having a hard time finding the computer through. I got it kind of.
Okay, but do you want to present from your?
Yeah, I can present that.
Okay, one thing because you're next. So you're started. Okay. Thank you.
You can deploy any kind of robot, like you could deploy a drone or something like that.
Well, whatever the Zemo supports.
Yeah, exactly.
Yeah, yeah, you can deploy it, and it's just that what we have is template interface. So you just go in there. We have all the Scenic code that controls the world for you. All you really need is having the code that relates to your own robot. Yeah, because each robot is different. Yeah,
the girl.
Oh,
yeah.
It's down
It's
right.
The push.
The network, the whole data center. I didn't realize you were
Sorry.
on the.
So I'm not connecting
The
to
merger
my
to the main
computer for
Yeah.
the machine,
On
but
one
not
hand, we have the template interface.
right now.
Oh,
I'm
it's not
connected.
supposed
On
to.
the other hand, we have the
Yeah, so I can't connect
to the
through
Sawyer
VS Code,
robot arm, the
but
big red robot arm.
so I can't like show any of the
So
like
that you have
code examples.
It's okay.
But I can just give like
Yeah.
a visual
Yeah.
demo.
And what we also
Okay,
have.
I mean at least this one.
What we also have that's being in review process right now, PR in review. There's like a general template interface for just like writing any Scenic template. So that should also be helpful. Yeah.
And you'll have to connect to the Zoom meeting so that you can.
Oh, okay.
It's the breakout.
Yeah, I think I found it. Oh wait, no, it's the wrong
Breakout
one.
one. You go down to schedule. Today.
Okay.
Keep going up. If you can just mute yourself and turn your sound off too.
Okay. 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 So,
Let's see if you can see.
okay, cool. Yeah. Okay.
And, are you sharing your screen?
Oh,
In
on
Zoom.
Zoom.
Yeah.
Desktop. I mean, I hope it shows the other desktop because, okay, we'll just find out. Yeah, okay, great. So, yeah, so what, something I did in Scenic was, interface Airstone with Scenic, and basically, what that means is that you can, control drones and spawn objects into Airstone, using Scenic. So, I made like a few example scripts here. Yeah, so I'll start with one example. The most simple example Just get it open. So yeah, I have this just like very simple. The drone just flies between positions. That's the first one. Yeah, so if we go here, actually let me disconnect from the drone. We just have the drone flying to the positions. Right now though, I can't really show, or maybe I can show the code because of the like database issue. I can't connect my VS Code to this, but maybe I can show just an example. Well,
I think it's fine, Mary. Just show some
yeah, so
capability.
block, yeah, position to position, very simple. And I also have another example. This one generates a world, like some parts in the world, and has the drone generate flying between a random order of the pops of the part. So if we go here, just gonna generate it. Oh yeah, I just moved the camera. Maybe I can just no, I'd actually go. It's happening over there. Traveling. Okay. So if we go here, oh, I see it. It's all the way, it's right here. So right now it's traveling between the random order of the tips of the cones. Yeah, and it's actually really easy to do in Scenic. Just yeah, it's just like a few lines of code where you just specify the object and I have a behavior that you can use and which makes the drone fly. And then I'll just give another example too. We can try to put in the flavors one, but I think it's a very simple one. Okay, here it is. And then let's go back to the beginning because the drone is, or maybe I should just restart the program. So yeah, I'm just gonna restart the program so we can actually like just be back at base one. Oh. Never mind. I think AirSim something happened.
Well, maybe we can just stop there. Maybe.
Yeah. Oh, I actually know what the issue was, but yeah, I don't know why it's happening, but well, I do know why it's happening, but I can't like I have to load in specific AirSim settings for this one, but
That's okay.
I can't load them into the database.
Okay. Thanks for having me. Okay. All right. So questions?
Oh, let me stop. I think I'm sharing. Okay.
Yeah, I think you've stopped. It's good. Thanks. Okay, so in the last 10 minutes or so, we have time to just discuss the use of Scenic in different domains like this, what kind of things people are interested in, maybe that we haven't been able to do so far that you'd like to do in Scenic. So we saw a bunch of examples of various kinds of robots. We saw also drones. And I don't think the Deutsche Bahn people ended up being able to make it, but people also use Scenic things like railway, et cetera. So and open the floor for a discussion about there's some other kinds of domains you'd like to use Scenic in or are interested in and don't know like how feasible that would be, or are there any blockers to using Scenic in these kind of applications, that sort of thing.
Well, I did have this idea. Well, I had it a while ago. I talked about a very
10:22 a.m.
I'm not sure how feasible it is, but like building generation scenic with like you have like a room or like room generation, you have a room and you want to like have like a lot of different objects in the room. It's like, oh, I want like a bookshelf and I want like like a chance for there to be books on the bookshelf, a certain number of books on the shelf.
Right. So I think this is similar to what Kai was doing with the human support robot, right? You were there in the scenario you had, were you generating anything? The only things you were varying were the position of the table and the object to pick up?
The only thing was what I was generating the table and I was spawning the bottom on the table.
Okay.
The table itself is fixed, but the bottom can change.
I see. Okay. But then the rest of the room that was fixed.
Yeah, the rest of the room that was fixed, and because that was a pre-built map.
Right.
So that's why it was operating.
Yeah. So I guess, when we had Eric's example with the robot vacuum, right there, we were positioning furniture and things like that. So you could imagine extending that to doing things like building a whole room with lots of details and so forth. That is something that is not necessarily that easy to do in Scenic right now, right? It's not that convenient to say, you build a table by a desk by putting a table and then you have a computer on that and you have a mouse here and books here, et cetera, and arranging all of that. You can use Scenic syntax for that, but I think as Eric and maybe was it Kai, you were looking at like making cluttered desks and things like that.
Yeah.
There are some things that were awkward there because you might like to do things like create a pile of a bunch of objects and just have them heap up automatically, and Scenic didn't really have something to do that for you. So I think you ended up writing a helper function with
Eric came up with a pretty fast way.
Right. So there might well be things like that are not so convenient to do because we haven't really developed that complicated scenarios like indoor environments yet. So that could be something interesting to see, like what kinds of things could we add to Scenic to make that kind of situation or that kind of scenario easier to run.
Well, one of the things, on that note, one of the things I think that'll be fun, that'll be like a nice feature to have is to be able to, of course, this might actually end up being simulator dependent implementation, but I think there might be still something general to be done. So what happens is that, for example, in the HLR scenario, you have an indoor pre-built map.
Mm-hmm.
I think what would be great would be, be able to feed in Scenic the description file of this entire map, and for Scenic to be able to essentially generate its own sort of impression. Right. Yeah.
So that is something that some of the simulator interfaces can do, right? So like Mary's and AirSim does actually learn, like you saw in the Mary's, correct me if I'm wrong, right? But you were creating the cones in the back, right?
Yeah.
But those other buildings you saw were pre-built part of the map, right?
Yeah.
And the AirSim interface that Mary wrote does import information about where those are, so it knows not to put a drone inside those buildings, for example.
Yeah.
And the reason we don't do that, for example, in say the Carla interface, is just that information is not accessible through the Carla API, the positions of trees and things. So what we would like to extend it in that way, right? So if basically, for any of the simulators that we support, if it's possible to get that information out about the pre-existing objects in the world and get them into Scenic, that would be a nice thing to do, because then you can first of all avoid Scenic creating objects that intersect, right? But you could also do things like refer to existing objects, like, okay, I want to put the robot 1 meter ahead of this particular table, which is already in the world, right? It would be nice if you got a way of being able to refer to that table rather than just hard coding a position, something like that. But, yeah. So I think it's just a simulator specific kind of thing, right? Because different simulators have different format. I don't know in the case, Gazebo, is it URDF?
URDF for the object description. I think for the entire world, there's a .world file. I think that probably has description too.
At least URDF is a standard format, right? That multiple tools can read. So it might be more plausible to have a library to import that, right? Like we already in the driving domain, for example, the driving model can import open drive files, which is a standard format for road networks. So you could imagine having a URDF importer, right, that could read that and figure out, okay, here are all the objects and so forth.
And having URDF actually will also help us be able to get a precise shape of robots.
Right. So we would need that information for, not just static objects, but also, if you have objects with component parts. So this was something that came up last night, but not everyone was there. But one limitation of Scenic right now that is problematic for robotics is Scenic assumes the shapes of objects are static. So for like the robot arm example I showed, Scenic cannot keep track of the changing shape of the arm as it's bending the various joints. And so that means if you ask Scenic partway through a simulation, can one object see a different object? Scenic is going to use the shape from the beginning of the simulation, not the updated shape as the arm has moved. So we have no notion in Scenic of a compound object that's made out of different parts, which can move independently. But for robotics, that's quite common. So that would be something we'd be interested in looking into going forward. Like how can we add functionality to Scenic to enable encoding that kind of compound object? And one way, would be reading a specification like that from formats like URDF that already encode that.
Yeah, I think again on the note of robotics, and this just popped in my head, so it's not very refined, but would it make sense to be able to add to Scenic this notion of different coordinate frames? Because in robotic systems, you're working with transformers are flying all over the place.
Right. So Scenic does have that. That's what the oriented point thing is supposed to be used for. So you can define kind of local coordinate systems and express things in terms of those using oriented points and this relative to operator.
But would that be like a three-dimensional case?
Yeah, it's three-dimensional now in Scenic 3. So you can basically, like, if you imagine you have some robot arm that's twisted in some complicated way, right? You can have an oriented point which is aligned with the hand, and then you can talk about things in it relative to that.
Right.
But this is something that we should probably write like a tutorial on just how to do that. Okay. Because we don't have complicated examples of that.
Okay.
I don't know if we have any examples showing how you would use that in 3D. Maybe, but I'm not sure.
I think what might be able to be done is to essentially have, show like a program where you're spawning, of course, spawning a robot arm.
Yeah.
But then correspondingly you're spawning oriented point that aligns with the coordinate frames of each link of the robot.
Right. So it would be nice to be able to do that automatically, like from the URDF description or something.
Right.
Yep, absolutely. But that's why we introduced the oriented point concept, because we'll be able to do stuff like that.
Okay, although I have a question about the oriented point itself. So oriented point, because oriented point obviously sort of like has a specific orientation.
Right.
But it's not. But when the robot operating, it's not just the orientation, because if it's pointing somewhere, but you still have an X, Y, and a Z axis direction to worry about for the coordinates.
So an orientation defines like in Scenic, an orientation has all three angles, if you want to think of it in terms of Euler angles. So it defines a local coordinate system with X, Y, Z axes pointing in certain directions.
I see. So the 0, 0 would just be aligned to the Scenic global coordinate frame.
Right.
Got it.
Yeah. So like 0 is like, if you imagine like this is north, this is 0, 0, 0, right? And then if you have like a yaw, it's like this, and the pitch, and then rolls.
Okay, yeah.
Scenic, you can either express one using those three angles or some other means. But yeah, an oriented point like has all three of those. So it uniquely defines a local coordinate system. Yeah.
So quaternions also.
Yeah, internally we use quaternions, but it's not very convenient to talk about those when you're writing the scenario, right? Because nobody really, at least I don't think in terms of quaternions. So the way you can create a local coordinate system in Scenic is either through Euler angles, like the three I just described, or by building up a series of transformations. So you can multiply two things together. You can apply several transformations and build up some more complicated one. But internally, it's all done with quaternions.
So with robotics, when a lot of articulated, objects like the robot arm,
right,
would also have like their local coordinate system.
Right. I think
that's the idea.
Right.
Would you actually be able to import those coordinate system directly?
Right. I think that's what Kai was asking that, if I understood correctly. This is something we don't do right now, but would be very convenient, obviously, for robotic applications. So I think this is something we'll want to look at.
Well, I mean, one is to import,
right?
Import the URDFs. The other is just the import of the coordinate systems.
Right.
By themselves, even just relative.
Right. So I think if we get the information out from URDF or wherever, basically about what the orientation of each of the links of whatever parts of the robots are, then Scenic does have operators that allow you to express things in terms of those local coordinate systems.
I'm not specifically talking about robot arm. Let's just say this room, we have like 20 chairs, and then 20 chairs each one of them has their own coordinate system.
Sure.
Would you be able to import, let's just say original kind of simulator has some scene, that already come up preview, and you'll be able to import that coordinate system directly into Scenic now.
Right, yeah, so you can. So if you can imagine, basically what the interface to the simulator should do is it should say, okay, in this simulated world, there are these 20 chairs. Here's the position and orientation of each of those. Then Scenic knows about those. And then in Scenic, you can say things like, if I want to position something at 1, 2, 3, with respect to this chair, not the global coordinate system, Scenic has operators to let you do that.
Okay, so
Yeah.
you already have that.
Right, we have that. It's just a question of getting in the information about what those local coordinate systems are. But once we have them, then Scenic has operators to let you use them, express things in the and convert between different ones. Yeah. Great. All right. Well, thanks everybody for the discussion and the talks. So it's time for the coffee break now, I think, right? 10:30? Yeah.